Welcome to this Inside Food Safety Training module. Today, we'll walk through 5 real food safety incidents that occurred in production environments, including allergen, physical, chemical, and temperature-related failures. We'll break down each incident using structured root cause analysis, review the corrective and preventive actions taken, and connect every case back to HACCP principles and prerequisite programs. By the end of this session, you'll understand not only what went wrong, but how strong systems, monitoring, and verification prevent these issues from recurring. This slide provides an overview of what we will cover in today's training session. The agenda is designed to guide participants through a structured learning path, moving from real-world incidents to root cause analysis and system-level improvements. 1. Real food safety incidents. We begin with 5 real incidents drawn from common failure points in food manufacturing. Undeclared allergen, metal contamination, sanitizer overconcentration, cold storage temperature deviation, additional operational deviations. These examples help trainees understand how hazards emerge in day-to-day operations. 2. Root cause analysis. For each incident, we break down the underlying causes using structured tools such as evidence-based investigation steps. This section reinforces that deviations rarely have a single cause. They are usually the result of multiple system weaknesses. 3. Corrective and preventive actions, CAPA. We review the corrective actions taken to restore control and the preventive measures implemented to avoid recurrence. This includes equipment repairs, monitoring upgrades, SOP updates, staff retraining. 4. HACCP and PRP connections. Each incident is mapped back to the relevant HACCP principles and prerequisite programs, helping trainees understand how real-world failures connect to the food safety plan. 5. Key takeaways. We close with a summary of the most important lessons from the session, focusing on early detection, strong verification, effective communication, and continuous improvement. On this slide, we're reviewing a metal detector failure that occurred during production. The detector alarmed correctly, but the reject mechanism did not activate, meaning the test piece stayed on the line. The last successful reject test had been completed 45 minutes earlier, so product continued running during the failure. This type of incident is considered a critical control point deviation because it creates a physical hazard risk. All affected product must be placed on hold, the equipment must be inspected and repaired, and the metal detector must be retested before production can resume. On this slide, we're reviewing the immediate actions required when a metal contamination risk is identified. The first step is to stop the production line right away and place all potentially affected product on hold. Next, the metal detector must be retested using all test pieces, and the reject mechanism should be inspected to confirm whether it failed mechanically or pneumatically. A full line clearance is performed to remove any suspect product, and the deviation is documented as a HACCP failure. These immediate actions are essential to protect consumers and maintain regulatory compliance. Let us look at the root cause analysis for the metal detector failure. Although the detector alarmed correctly, the reject arm did not activate. The investigation found a loose pneumatic connection that prevented the arm from moving with enough force to remove the test piece. Contributing factors included weak preventive maintenance, incomplete verification checks, and a delay in stopping the line after the failed test. This incident shows why root cause analysis must look deeper than the initial symptom, and why strong maintenance programs and operator training are essential for HACCP reliability. Now that we've identified the root cause, let's review the corrective actions taken to restore control of the metal detection HACCP. The pneumatic fitting on the reject mechanism was tightened and secured, and the air pressure was verified to ensure the arm could fully activate. A complete validation was performed using all 3 test pieces, and the detector passed consecutive reject tests before production was allowed to resume. All product from the affected 45-minute window was evaluated and handled according to the risk assessment. Finally, the deviation was fully documented, and a maintenance work order was completed. These corrective actions ensure both immediate safety and long-term system reliability. In this slide, we're looking at an undeclared allergen incident caused by a label changeover failure. A no egg label was mistakenly applied to a product that actually contained egg. This type of error is extremely serious because it can lead to allergic reactions, regulatory violations, and even product recalls. Incidents like this highlight the importance of strict label verification, proper changeover procedures, and cross-checks between production and quality teams. Let us review the immediate actions required when an undeclared allergen incident is discovered. In this case, a product containing egg was incorrectly labeled as no egg, which is a high-risk food safety failure. The first step is to stop production and place all affected product on hold. Distribution must be blocked, and a full traceability check is started to determine which lots were impacted and whether any product has already shipped. The QA and production teams verify all labels, inspect the line for changeover errors, and document the deviation. These immediate actions are essential to protect consumers with allergies and to maintain regulatory compliance. Now, we review the root cause analysis and corrective actions for the undeclared allergen incident. The investigation found that the wrong label roll was loaded during changeover, and the line clearance was not fully completed. There was no dual verification, and similar packaging artwork contributed to the mix-up. Corrective actions included removing and relabeling affected product, implementing two-person label verification, adding barcode scanning for allergen-containing items, and updating the changeover procedure with mandatory sign-offs. This incident reinforces the importance of strong allergen controls, proper changeover checks, and consistent operator training. In this section, we're reviewing a foreign material contamination incident involving plastic fragments found in finished product. The contamination was traced back to a damaged equipment component, creating a physical hazard that could lead to consumer injury and potential product withdrawal. This incident highlights the importance of preventative maintenance, routine equipment inspections, and strong foreign material control programs to protect product integrity and consumer safety. Now we analyze the immediate actions required when foreign material contamination is suspected or confirmed. The first step is to stop the production line right away and place all potentially affected product on hold. A full line clearance is completed to remove any suspect product. QA inspects the equipment to identify the source of the contamination. Detection systems, such as metal detectors or X-ray units, are verified to ensure they were functioning correctly. All findings are documented, stakeholders are notified, and the incident moves into root cause analysis. These immediate actions are essential to protect consumers and maintain food safety compliance. Let's analyze the root cause analysis for the plastic contamination incident. The investigation found that a damaged plastic component on the equipment had fractured during operation, allowing small pieces to enter the product stream. Contributing factors included missed wear during routine inspections, gaps in preventative maintenance, and the absence of a checklist focused on plastic component integrity. The facility also identified system weaknesses, such as not using metal detectable or color-coded plastics, and inconsistent documentation of equipment condition. This incident highlights the importance of strong maintenance programs, thorough inspections, and early detection of equipment deterioration. Now that we've identified the root cause of the plastic contamination, let's review the corrective actions taken. The damaged plastic scraper and guard were replaced with metal detectable blue components, and all similar parts were inspected for integrity. Preventive maintenance schedules were updated, and daily visual checks were added to detect wear early. A foreign material inspection checklist was introduced, and operators received refresher training on identifying equipment deterioration. These corrective actions strengthen the facility's foreign material control program and ensure long-term product safety. For our next incident, we're reviewing a chemical hazard incident involving sanitizer overconcentration. During routine verification, the QA technician found sanitizer levels at 1200 ppm instead of the 200 ppm target. This excessive concentration created a risk of chemical residue on food contact surfaces and potential product contamination. Such incidents highlight the importance of proper dilution systems, daily verification, and staff training to ensure sanitizer strength remains within safe limits. Let's check the immediate actions required when sanitation concentration is found to be above safe limits. Sanitation activities must stop right away, and the affected area should be isolated to prevent contact with food or packaging. All equipment is drained and rinsed to remove excess sanitizer. Then a fresh solution is prepared at the correct concentration. QA verifies the new concentration using test strips or a digital meter, and the deviation is documented. Any product that may have been exposed is placed on hold, and sanitation staff receive retraining on proper dilution and verification procedures. These immediate actions protect both product safety and worker health. Now we review the root cause analysis for the sanitizer overconcentration incident. The investigation found that the operator used undiluted concentrate instead of the premixed solution, resulting in excessive sanitizer strength. Contributing factors included a calibration issue at the dilution station, missing secondary checks, and inadequate labeling on concentrate containers. The facility also identified system weaknesses, such as reliance on manual mixing and inconsistent documentation of concentration checks. This analysis highlights the importance of verification, clear labeling, and automation to maintain safe chemical control. Corrective actions included equipment upgrades. An automated dilution system was installed to prevent manual mixing errors. Sanitation staff received refresher training on proper dilution, equipment use, and chemical handling. 2. Verification and checks. QA now performs daily sanitizer concentration tests using both digital meters and test strips. A standardized chemical control procedure was introduced, including documented verification before sanitation begins. 3. Labeling and safety improvements. All chemical containers were updated with clear, color-coded labels to prevent confusion between concentrate and diluted solution. New warning signs were added at the dilution station to reinforce safe handling. 4. QA oversight and training. QA increased oversight during sanitation setup and chemical preparation. Operators now receive ongoing training on chemical control, verification steps, and deviation reporting. A review and documentation checklist ensures every step is recorded and signed off. Next example introduces the cold storage temperature deviation incident. During a routine monitoring, the cooler was found operating at 9 degrees Celsius, exceeding the critical limit of 4 degrees Celsius required for refrigerated foods. The high temperature alarm was triggered, and QA immediately placed all affected product on hold. High temperature detected. Digital monitoring system recorded a sustained temperature of 9 degrees Celsius. Alarm panel displayed high temp alarm. Deviation duration estimated at several hours. Product at risk. Perishable foods such as meat, dairy, and ready-to-eat items were exposed to unsafe temperatures. Increased risk of pathogen growth, spoilage, and reduced shelf life. QA initiated a product safety assessment. Cause investigated. Maintenance inspection revealed ice buildup on cooling fans. Air vents were partially blocked, restricting airflow. Condenser performance was reduced due to overdue preventive maintenance. Potential impact. Possible product spoilage and financial loss. Risk of product recall if safety cannot be verified. Potential regulatory non-compliance with cold storage requirements. Let's discuss the findings from the investigation into the cold storage temperature deviation. The goal is to identify the underlying causes that allowed the cooler to reach 9 degrees Celsius, placing perishable food at risk. Primary root cause. The investigation confirmed restricted airflow due to ice buildup on evaporator fans. Frost accumulation reduced cooling efficiency, causing the temperature to rise above the critical limit. The cooling system could not recover without manual intervention. Contributing factors. Preventative maintenance was overdue, and the condenser had not been serviced according to schedule. Product was stacked too close to air vents, blocking circulation and worsening the temperature rise. The temperature sensor calibration had not been verified after recent repairs, reducing accuracy. System weaknesses identified. No weekend or off-shift monitoring, allowing deviations to go unnoticed for extended periods. Alarm response was delayed due to unclear escalation responsibilities. Maintenance logs were incomplete, making it difficult to track service history and identify early warning signs. Let's outline the corrective actions taken after the cold storage temperature deviation incident. These actions address both the immediate equipment failure and the systemic gaps that allowed the deviation to persist. 1. Equipment and maintenance. Evaporator coils were defrosted and airflow was restored while cooling system components were repaired and serviced to ensure proper function. A revised preventative maintenance schedule was implemented, including condenser cleaning, fan inspection, and vent checks. 2. Monitoring and alarms. The cooler was upgraded with continuous digital temperature monitoring. Remote alarm notifications were activated so QA and maintenance receive alerts instantly. Alarm thresholds and response times were reviewed to ensure early detection. 3. Procedural controls. Added off-shift and weekend temperature checks to prevent long periods without oversight. Updated the escalation protocol to ensure immediate supervisor and QA notification. Implemented a cooler access log to track door openings and identify temperature-impacting behaviors. 4. Training and documentation. Staff received refresher training on cold storage critical limits and deviation response. Emphasis was placed on recognizing early warning signs and reporting issues promptly. Maintenance and monitoring documentation templates were improved for consistency and traceability. This final slide connects all 4 incidents back to the core elements of HACC and the prerequisite programs that support it. Each deviation we reviewed, undeclared allergen, metal contamination, sanitizer overconcentration, and cold storage temperature deviation, demonstrates how HACC and PRPs work together to prevent hazards. HACC principles. Hazard analysis. Each incident represented a different hazard category: allergen, physical, chemical, and biological. This reinforces the importance of a thorough hazard analysis during HACC development. Critical control points and limits. Label accuracy is a CCP for allergen control. Metal detection is a CCP for physical hazards. Chemical concentration checks prevent sanitizer misuse. Cold storage temperature limits protect against pathogen growth. Monitoring. Failures in monitoring contributed to each incident. Missed label checks, skipped detector tests, inaccurate titration, and delayed temperature response. Corrective actions. Across all incidents, corrective actions included product holds, equipment repair, retraining, and documentation updates. Verification. Calibration, internal audits, and record reviews ensure the system is functioning as intended. Record keeping. Logs and documentation provide traceability and support regulatory compliance. Prerequisite programs, PRPs. Label control. Prevents undeclared allergens. Sanitation and chemical handling. Prevents chemical contamination. Preventative maintenance. Prevents equipment-related hazards like metal fragments or cooling failures. Storage and temperature control. Ensures cold chain integrity. Supplier and material handling. Supports raw material safety. Training and competency. Ensures operators understand critical limits and deviation response. Let's wrap up with the key learnings from this module. Across all 4 incidents, one theme stands out. Strong systems prevent small issues from becoming food safety failures. Early detection is critical. Alarms, checks, and verification steps only work when we respond immediately. Root cause analysis showed that equipment wear, airflow obstruction, and missed maintenance can quietly build risk over time. Corrective actions restored control, but the real value comes from preventive measures: continuous monitoring, remote alarms, weekend checks, and consistent documentation. Together, these practices strengthen our CCPs, reinforce our PRPs, and build a culture where food safety is protected every day.